So here is an example question of the style that you might get in an exam. Maybe slightly different language used, but the key elements are we're given some expression which contains coses and sines. We're being asked to transfer that or change that into the form where it's a single sine or a single cos in this part here. So first example I'm going to do is a single cos, but I will do an example in a minute with a sine in there instead. There's no major difference except just being aware of which identity to use. There is a funny symbol here. That's just an alpha. Don't panic. It looks like that. That won't always be written as an alpha. I will write it as an alpha in the examples I am doing and in the questions. But it could be given as a different letter, and the same with the K. That's sometimes in some sources used as an R. Don't worry. Something in the form a number times cos of x plus or minus some amount here. That's the key things to watch out for. You also need to be careful. I've highlighted in orange as ever with my ranges. If you're working in degrees or in radians at this point, I'll mention when that comes back in, but just check, am I in degrees and in radians? Everything I'm going to do at the moment is all in degrees, but there is no reason that you couldn't get a question in radians. It's just a tiny change at the end where you'd be working in radians. Now, to start this question, well, I don't really got any good places to start, but I've got an angle here which are added or subtracted. So actually I'm going to start with that part where I'm going to write out what on earth that could be expanded to be. Now, thinking back to our trig identities, and you can look up your formula sheet for this, but cos of x minus alpha, or cos of a plus b, is the formula that's in your formula sheet. And you might actually want to just sketch that above. Cos of a minus b, well, you can check it back in your formula sheet and read it off, is just cos of a, cos of b, plus, and that's really important, remember with cos, the sign swaps, sine of a, sine of b. So that's from your formula sheet, just look it up. Applying that to this, we've got cos of x, cos of alpha, plus sine of x, sine of alpha. Now all of that's in a big bracket with the k out the front, so let's multiply that out. I'm actually also going to put the alpha term first. So this is k cos alpha cos x, and it doesn't matter to swap my terms over, we're multiplying, doesn't matter which order we multiply in. Plus k, because we're multiplying in by that k, and bring the sine alpha to the front, sine x. Now, this is really important because somehow we've got to write this thing in this form. Well, our kind of stepping stone to doing it is writing this thing in this form. And noticing here what matches up. Well, here's our sine x. So the thing in front of the sine x there must match the thing in front of the sine x there. So from the purple bit, we have that k sine alpha is equal to 3. Well, we can play the same game with the other bit. We can look at the thing in front of the cos x. Well, that is k cos alpha. Must match up with the thing in front of the cos x up here, which is minus 4. So we have k cos of alpha equals minus 4. We're making some progress. We've got some vague relations to sine and cos, which involve just a number and some letters. We do have two unknown things, so we've got a k and an alpha to find. So we've got to find some ways to make these cancel out. Well, we've already seen the tricks that we're going to use for this. Because if I do k sine alpha squared plus k cos alpha all squared, that's the same as doing this thing, which is 3 squared plus minus 4 all squared. Just literally taking that thing is the same as that thing. So this thing squared is the same as that number there squared. And same for the k cos alpha. Why does that help? Well, that helps because when we expand this out, remember, we went through our steps for that a second ago. I'll bring that back on. Here's what we did in the starter. We had something like k sine x squared plus k cos x squared. Oh, my bracket was in the wrong place. Apologies. When we work our way through all of that, we get k squared. And actually, it's totally acceptable in doing this math to know that fact, that this line here goes to k squared. If you want to write all the detail and put in these in-between steps here, you're very welcome to do that, but it's absolutely not necessary to do that. So k squared here is equal to, well, 3 squared is 9, minus 4 squared is 16. So we get k squared equals 25. And so k equals 5. Now, you might say, could it be minus 5? Because we've got square root here. The other detail in my question, which might well, or should have been there, is that k is greater than or equal to 0. So this should be a positive 5. I should have put that detail up in the question to start with. Apologies, it will be there for the next few. Now, that's got as our k value. There are a couple of ways to get your alpha value, but the way that avoids getting this wrong is to actually do the following. And the reason you're likely to get it wrong is you need an alpha that makes this positive and this negative, and just watching all the details with that. The easiest way to do it is to do k sine alpha over k cos alpha. Well, like we showed, the k's cancel out. So that is tan of alpha. But this thing here is also, well, sine over cos. That is 3 over minus 4 is equal to tan alpha. Now, we've got a complex consideration to make here. And this is where cast probably wins over graphs. So if you haven't been drawing cast diagrams so far, this is a time when cast comes in quite handy. But it's not a complicated use of it. So we've got a tan which is negative. So that's either up in this section or down in this section. But we need to decide which one we're in. Well, going back, we also know that our sine was positive, which is true there, but not true there. And our cos was negative, which is true there, but not true there. So we're up here in this section of the graph. So when we find our relative acute angle, we want to do 180 minus that relative acute angle, and that will get us to this section. Now, you can deduce all of that using graphs, but this is the one time that cast really comes into its own. So I am going to do it that way. I know for some of you this will be a bigger transition because you've not been using cast up until this point. However, I do recommend just figuring out how to use it. So our relative acute angle is tan to the minus 1 of 3 over 4. And if you put that into your calculator, you get 3.69 with more digits. And we want 180 take away that angle. So our alpha, is equal to 180. Oh, running off the screen. Take away our 36.9, etc. And that gives us 143.1 degrees. Now we know our k and we know our alpha, we are finished because we can put them in there, we can run that back to there, and we were just comparing, so everything works out. So let's write our final answer. We have that minus 4 cos x plus 3 sin x is equal to, well, our k, 5 cos, and I'm just looking at this form up here, of x take away whatever we find alpha to be, which is 143.1 degrees. And there we are. That is our finished answer. We have actually managed to compare the two, figure out our k and our alpha, and write ourselves a nice simpler version. We've taken this cost sine thing, simplified it into a basic cost curve. And you can check this. This is actually one of the great things. You can always check your answer with these. So if you do 5 sine 143.1, it should give you something that rounds very closely to 3 on your calculator. And if you do 5 cos 143.1, it should give you something that rounds really closely to -4. So actually, it's a really good thing. You can go back. You can always check your answers when you do these. Now, I've done this one in huge depth. The next two I hope to do a little bit faster, with slightly less kind of explaining along the way. But hopefully that gives you a good idea of how to work these out.